Electronics is a science that applies these tubes to the service of man, to the speeding of production, to the winning of the war. To understand how electronic tubes work, let's take a good look at one of them, one that's representative of its species. This is a diode, a typical two-element electronic tube. Let's get inside it. In fundamental operation, it resembles an ordinary single-pole switch, a switch that can connect, for instance, this battery and its motor load. One power lead comes to the anode, the other lead goes to the cathode. When this switch is open, the contacts are insulated from each other by a vacuum, or by some inert gas inserted into an evacuated tube under low pressure. To close this switch electronically, all we need do is heat the cathode and give the anode a positive potential. Then here's what happens. As electrons are emitted from the surface of the heated cathode, being negatively charged, they fly at tremendous speed to the anode. In this way, a current-carrying path is formed, which closes our electronic switch and permits our motor to operate. You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus. Now, at this point, you may ask, if an electronic tube is basically just a form of switch, why is electronics hailed today as the technique of a new engineering era? To answer that question, let's review 6 of the basic things that we can do with this new kind of switch. In the first place, we can rectify current with it, converting AC to DC. We can do this merely by connecting an electronic tube in series with an AC circuit. As you study this circuit diagram, note that only each positive half wave of AC voltage will now produce a current. When the anode is negative, the electrons are repelled and no current flows. In other words, because only the cathode can emit electrons, we have here what amounts to a one-way street. We can visualize the result of the tube's rectifying action with the aid of these 2 oscilloscopes. The one on the left shows alternating current coming in. The one on the right shows pulsating direct current going out. The applications of this basic rectifying principle are many and important. Here's one of them, changing AC to DC on the nation's electrified transportation systems. Here's another, rectification for electroplating operations of all kinds, operations possible only with direct current. Still another example, furnishing DC in steel mills for the driving of variable speed motors, such as the one controlling this giant ladle, or the ones driving steel conveyors with such precise control of speeds that danger of buckling and tearing and consequent mill damage is eliminated. Electronic rectification is also helping to build American air power by making available record-breaking quantities of aluminum for plane construction. From Arkansas mud to American air power involves a complicated conversion of material. Before pure aluminum can be extracted from this bauxite ore, direct current must be applied in a vital reduction process. To obtain that direct current from AC transmission lines, the ignitron rectifier is used. This Westinghouse electronic development changes vast quantities of AC to DC with higher efficiency than any similar type of conversion equipment. Today, it's the main source of current supply for the nation's great aluminum industry, an industry that has achieved a miraculous expansion to meet the demands of a world at war. Magnesium from seawater is another achievement of industry under the stress of war. Ignitrons used in the extraction process speed up the delivering of incendiary and demolition bombs to the centers of Axis production. Still another example of electronic rectification at work is the precipitron, a device for cleaning air electrostatically. This diagram explains how the precipitron works. The rectifying property of electronic tubes is used to apply a potential of 13,000 volts DC to tungsten wires and 6,500 volts DC to collector plates. As incoming air passes through the field of these wires, each particle of dirt receives a positive electrostatic charge. When the positively charged particle reaches the collector chamber, it's attracted to and deposited on negative plates. In this way, air is cleaned so thoroughly that dirt particles down to a 1/4 millionth of an inch are removed. This is a vital advantage today, not only in homes and public buildings, but in industrial plants of all kinds. For instance, in plants manufacturing delicate instruments, where air cleanliness is necessary for precision work. In workrooms where optical systems are assembled for a host of military purposes. In inspection rooms where minute parts must be closely examined under high magnification. Air cleanliness is vital, too, in film developing rooms like this one. To understand how electronic air cleaning helps here, let's go aloft in a reconnaissance plane. Click. 5,000 feet above the earth, a camera shutter opens and closes. Scores of square miles of enemy territory have been squeezed down into an image on a photographic plate. An image measured in inches instead of miles. On this photograph, a city might be covered by a tip of a finger. A speck of dust could hide a Nazi aerodrome. The rectifying tubes of the precipitron help make sure that dust doesn't sabotage military photography. Now, so far in this film, we've discussed only one of the basic things we can do with the electronic tube. We can use it to rectify. The second basic thing we can do with it is amplify. Here's how. Between the cathode and the anode of the two-element tube, which we diagrammed a while ago, we now place a grid. To this grid, we connect an input of some weak voltage which we wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens. Every time a negative potential is impressed on the grid, even though it be very minute, it has a large effect in reducing the number of the negatively charged electrons which would otherwise keep flying from cathode to anode. Conversely, when the grid is positive, an equally large effect is exerted in increasing the flow of electrons from cathode to anode. The important thing to note here is this. A small amount of power applied at the grid is amplified into a large amount of power in the anode or work circuit. This amplifying property of the three-element electronic tube is put to work in innumerable ways. Westinghouse electronic amplification now helps provide radio and radio telephone contact between airplanes and control stations on the ground, between ships and their communication bases, both afloat and ashore, between individual tanks and their tank force commanders, between firing line and headquarters, between Seadrome lights and night-flying pilots who can turn them on by radio signal. In the field of power engineering, electronic amplification permits the measurement and analysis of minute voltages, stepping them up to the point where they can be seen and interpreted on oscilloscopes. When this giant rotor is completed, its precise dielectric balancing will be made possible by amplifying tubes. Testing of these propellers for vibration fatigue will also be facilitated by electronic amplifying tubes. Up to now, we've considered two of the basic things that the electronic tube can do. It can rectify, it can amplify. A third thing it can do is generate. The term generate in this connection is meant in a general rather than a technical sense. A triode is connected for oscillation in the way shown here. The system then becomes capable of changing direct current into alternating current. Note that what we're doing in this case is amplifying in the usual way and then feeding back to the grid part of the amplified voltage. Continued repetition of this feedback results cumulatively in a strong alternating current. This electronic means of generating alternating current is important because it can produce very high frequencies, frequencies up to millions of cycles, far beyond the range of ordinary rotating equipment. A familiar application of this is the radio transmitter. This modern transmitting room of Westinghouse station KDKA is a far cry from the pioneering equipment of its famous predecessor. This scene reproduces an historic occasion, the first time a radio transmitter was used for large-scale public entertainment.
This is station KDKA of the Westinghouse Electric and Manufacturing Company. We are about to begin the reading of the presidential election returns between Warren G. Harding and James M. Cox. Stand by, please.
Here is a new, less familiar application of electronic high-frequency generation. High-frequency heating of 200,000 cycles per second is now used to flow tin as the final step in the electrolytic plating of steel strip. After steel strip comes from its electrolytic tin plating bath, it first passes through a washer, then between hot air drying jets. At this point, the steel strip has a coating of tin that is relatively dull and porous. Next comes a vital step. The strip is raised to the top of the heater unit housing, inside of which is a series of high-frequency coils. As the strip comes down through these coils, induced electric current causes heat, which flows the tin almost instantaneously, greatly improving its structure as a protective covering. Here's the result: tin plate that is mirror smooth, free from porosity, so perfect a protective covering that 1 pound of tin can now do the work of 3. Note the horizontal bars in this close-up. These are parts of one of the high-frequency coils that affect the tin flow. If you look closely, you can see the difference in texture between the porous tin entering the top of the coil and the shiny flowed tin leaving at its base. And these are the tubes that generate the high-frequency current which makes the entire process possible. Another important result of this new Westinghouse electronic process is time saving. Tin can now be flowed at a rate of more than 1,000 feet a minute. Here's another example of where electronic high-frequency generation is doing a job today. Dielectric bonding of plastic and plywood sections in a matter of minutes instead of days. As a result of this application, plywood-constructed PT boats can be produced more speedily. Dielectric heating also cures intricate plastic forms faster and better. Here, a dielectrically cured plastic piece is being given a stress analysis. Carrier current relaying also applies the electronic principle of high-frequency generation. Here's part of the equipment that does the work. This equipment makes possible an enormous increase in the speed with which transmission lines can be cleared of faults. Its effect is to increase the load-carrying ability of a system up to 50% or more. We've now illustrated 3 of the basic ways that the electronic tube can be put to work. It rectifies, it amplifies, it generates. And here's a 4th thing it does. It controls. This diagram illustrates one of the principal mechanisms of electronic control. We use the grid here not to amplify a weak signal, but to control the flow of power to a machine. To do this, we connect the control circuit in such a way that it becomes a function of temperature, speed, time, or any other variable. As a result, grid potential is varied, and the work circuit is automatically closed, modified, or opened. And we can do all this with split-second timing and incomparable precision. Take, for instance, this electronically controlled spot welder. Without sound, without friction, without flame, electronic control on this equipment makes and breaks contact with split-second timing. Seam welding, too, is electronically controlled. As a result, plane parts today are being literally sewn together with electric current as thread. But welding, of course, represents only one opportunity for electronic control. Automatic stepless regulation of motor speeds is another application. Without the smooth acceleration which such control makes possible, delicate materials, such as the capacitor windings being handled here, might be broken under the shock of starting and abrupt speed changes. Now for still another basic thing that the electronic tube can do. It can also serve as a bridge to transform light into electric current. Here's how. We replace the ordinary heat-activated cathode of a two-element electronic tube with one made of photosensitive material. Light can now replace heat as the stimulator of electronic emission. The stronger the light, the greater the electronic emission, and consequently, with the aid of an amplifier, the more power flowing through the work circuit. This is important because it means that photoelectric tubes can function as light relays and so be given an almost infinite variety of jobs to do. Scanning the soundtrack of the talking motion picture film you're listening to right now is one of them. Another is the television camera. The iconoscope used in this camera is merely a special form of electronic tube. Product and process control is still another application. In this plant, a phototroller automatically stops a conveyor belt every time a lightning arrestor comes to its point of inspection. Here, a Westinghouse electronic eye inside the metal housing spots pinholes in metal strip as it comes from the rolls, automatically operating a relay that rejects defective sections, dropping them out of the production line without a moment's loss of working time. One of the most important basic things that the electronic tube can do remains yet to be listed. Besides transforming light into electric current, it can also transform electric current into light. The cathode ray tube is an application of this property. Through the aid of this tube, an electron beam is able to recreate an original image on the screen of a television receiving set. The electronic X-ray tube indirectly also transforms electric current into light, and by its effect on photographic plate, into light images. Here's how an X-ray tube works. A high potential ranging up to 300,000 volts or more is applied between the anode and cathode. Electrons are emitted by a focusing cathode. Due to the extremely high voltage, the electrons hit the anode with tremendous impact and cause the emission of waves of exceptionally high frequency. These high-frequency waves do three useful things: penetrate, excite fluorescence, or affect photographic plates. As a result, doctors can now study human internal organs by means of the fluoroscope. Or by means of radiography, they can photograph them. Industrial X-ray today is also playing a vital role, detecting porosities and fissures in welded metal seams, examining heavy castings for invisible internal weaknesses. But X-ray isn't the only example of electronic usefulness in the conversion of current into light. The whole field of modern fluorescent lighting represents another application. So does the field of ultraviolet radiation. Harmless-looking tubes like this one have a deadly effect on bacteria and other forms of microscopic life. In this demonstration, Parmesia rather than bacteria are about to be subjected to Sterilamp rays. Notice what happens. The Sterilamp today is becoming increasingly important, both as a servant of public health and as a device for the preservation of perishable goods. So many and so varied are the applications of electronics that a single film like this can mention only 1 in 1,000. We haven't even mentioned, for instance, radar, the electronic development that helped save Britain during the decisive weeks of the German aerial blitz. Here's what happened. Ultra-high frequency waves were broadcast into the skies from English defense stations. When enemy planes approached in the darkness or in the fog, these waves would reflect back to the transmitting points, thus giving warning to the defenders of Britain, permitting anti-aircraft batteries to swing into action and RAF planes to rise for combat. Whenever Hitler's bombers attacked, at whatever altitude, from whatever direction, British interceptors were waiting for them. As a result, the Luftwaffe was blasted from the English skies and the tide of war turned. Yes, the electronic tube, in essence, is only a switch. But what a switch! It rectifies, amplifies, generates, controls, transforms light into electricity and back into light again. These tubes that look so mysterious are essentially simple in operation, incredibly rugged and sure in application. They open and close all forms of electronic circuits as swiftly as the lightning flash and as silently as the passage of time. In the world of today, they're helping us to win a war. In the world of tomorrow, they bid fair to lift all of us to new levels of achievement, comfort, and security.